We're going to start with chapter 1, which is chemistry in our lives. So clearly, we use chemistry in all kinds of areas. In medicine, forensic science, as you saw there, obviously in our body, we use chemistry to help us do several processes throughout our body. So chemistry really is the study of composition and really the structure and reactions of matter. And when we talk about matter, matter is really anything that sort of occupies space and has mass. And a lot of times what we look at is sort of, sometimes how that matter sort of changes states. This is a very big part of what we see in chemicals, chemistry, and also reactions. There's three sort of states that we commonly sort of come across. One is solid, one is liquid, and obviously there's the gas state. And typically speaking, in the solid state, everybody is, for the most part, packed in there pretty tight to one another. A lot of times things in the solid state are very dense, packed in. One exception, as we'll talk about, I think, along the way, is water. Water is an exception of that. It's not really packed in. It's actually less dense in solid state than, say, liquid. In the liquid state, we still have everybody still relatively, close to one another. But there definitely is a little bit more room for movement, if you will. And that's why when we think about liquids, they're fluid, right? And that's really because the atoms, the molecules, they're able to actually pass one another in that state, as opposed to in the solid state where they're really just kind of locked in. They don't have a lot of that movement past one another, and they basically kind of are stuck in place. Gas, on the other hand, when we get into the gas sort of phase, we are really at the point where everybody has completely broken apart from one another. They're flying around. And as we'll talk about when we do get to the gas chapter, as they're flying around, there's like collisions that occur with the container. And that's really what we associate pressure of gases with. As they collide, the more collisions that they do as they are flying around, the more pressure that we sort of see. When we kind of go from solid to liquid to gas, there are different sort of names that we talk about as we do that. When we go from solid to liquid, that is the process of melting. Like if you have an ice cube, right? You put it out there, it starts to melt. You feel bad about your ice cube, right? So you grab up all the liquid there and put it back in the freezer. So going the opposite way, going from liquid back to solid, that is the process known as freezing occurring. When we go from liquid to gas, that is the process of evaporation, or sometimes referred to vaporization. When we go from the gas state back to the liquid state, that is the process known as condensation. There's also a process where we could go directly from solid to gas and actually skip the whole liquid part, and that is what is known as sublimation. Going back gas to solid, we could also do that when, once again, here we would be skipping the liquid phase, and that's actually what is known as deposition. So a lot of what we look at in chemistry is, the different states of matter, these different transitions that occur with matter. And really how things change. And a lot of times we relate, how these things change to something like energy, for example. As I go from, say, solid to liquid to gas, would I need to put energy in to do that, or would I need to take energy out to do that? It is a process. All those processes are processes where we would put energy in to do that. If you think about the ice cube example, when you take it out of the freezer where we got your ice cube from, I suppose, as it's sitting out there, is picking up heat and energy from the surroundings, if you're not melting it yourself, right? And it starts to melt. If you take some liquid water, right, and you want to make some pasta, you put a fire underneath it, right, and it starts to boil, right, and the steam that's coming off of that is the water that has now transitioned to the gas phase. And those are all processes where you would put energy in. So energy would go in, and all these processes are absorbed. And when you do any processes where energy is really put in or absorbed, they're sometimes referred to as endothermic processes. And the opposite would be true if we actually started in the gas phase and really worked our way backwards. If we went from our gas to liquid to solid, those are all processes that would require us to basically release energy. So if you think about it, if we're starting in the gas phase, everybody's flying around really, really fast. If those guys lose energy, they're going to fly around a lot slower. And as they fly around a lot slower, frankly, they're going to stick to each other and drop out of the gas phase and really back into the liquid phase. And in the liquid phase, they'll still have a little bit of energy, but if you continue to take that energy out, they're going to kind of slow down, and now they're going to kind of be stuck into place as you release all that energy from the system. So going the backwards way, gas to liquid to solid, this is all what are referred to as being energy is being released. And those processes are what are referred to as being exothermic. Questions on that there? One last sort of question here, as we kind of jumped on a tangent here, but one last question is, does melting and freezing occur at the same temperature or different temperatures? It actually occurs at the same temperature. So the process of melting and freezing will actually occur at the normal, what is referred to as the melting point or the freezing point of a substance. And it does occur at the same temperature. So for example, water will freeze and also melt at 0 degrees Celsius. At exactly 0 degrees Celsius, you actually have a combination of both phases happening at the same time. You got a little bit of solid, you got a little bit of liquid. It's not, for example, for water until you get a little bit above 0 degrees that you actually kind of get liquid water. And it's not until you get a little bit below 0 degrees that you actually have ice. But dead on at 0 degrees, which is that freezing point, melting point, you do have both of those phases together, and it does occur at the same temperature. The defining difference of what will happen at that point is actually energy. So if you continue to put energy in at 0 degrees, your ice cube will continue to melt and eventually reach liquid water. If at 0 degrees, you continue to take energy out, like actually put it in the freezer, or actually rip out the energy from your ice there, it will continue to go to the solid and make solid and continue that process. So both melting and freezing occur at the same temperature, and the same deal here with evaporation and condensation. They actually also occur at the exact same temperature, and that is what is normally the normal boiling point of a substance. At the normal boiling point of a substance, that's when you get it to go into the gas phase. And the same process occurs there at exactly, for example, 100 degrees Celsius, which is the boiling point for liquid water. At exactly 100 degrees Celsius, you actually have, again, both phases there. You have the liquid phase and you have the gas phase. And again, it's not until you get a little bit above 100 degrees Celsius that you really fully transition into the gas phase, not until you get a little bit below that you are still in the sort of liquid phase. The determination of what's going to happen, again, is related to energy. If you put more energy in, you will continue the process of boiling and going into the gas phase. If you remove energy at that point, you will go into the process of condensation and create some liquid water. Any questions on that? So in addition to matter and different states of matter, obviously chemistry is study of composition, what everything is made out of, the structure, how it's put together, properties, like what characteristics do we have, and reactions, how do they behave. As I mentioned earlier, matter is really what everything is made out of. And it's basically anything that has mass and occupies space. Chemicals are substances that have the same composition no matter where they're found. So chemicals and compounds and molecules are things that we talk about a lot in chemistry. And as we'll talk about, there is actually a difference between a few different things. There is a difference between elements, molecules, and compounds. And these are oftentimes words that sometimes sort of mix some people up as to what's the difference between them. So really, as we'll talk about, elements are really the basic units of everything, right? They're the basic units of really everything. The basic unit of a element is an atom, and as we'll talk about in a later chapter, atoms have protons, electrons, and neutrons. Now, elements obviously are on the periodic table. You could think of elements as really kind of like the alphabet, right? There's only like 26 letters, I think. They haven't added any more, hopefully, but there's only 26 letters. But you can rearrange those letters in all kinds of different combinations, and it gives you all kinds of different words, right? And same thing with elements, depending on sort of the arrangement, what elements you put together, how many of each element, they do give you different molecules and compounds. The two words here are usually very often confused by people. So let's talk a little bit about those things. A molecule, by the way, that's what's in toothpaste, in case you're curious, but a molecule is basically the simple combination of two or more atoms. So a molecule is a combination of two or more atoms. The deal with that is they can be two or more atoms of the same element, or they can be two or more atoms of different elements. But the basic definition is you just need at least two atoms together or more. And the reason for that is there are certain elements that actually come as molecules. So there are certain elements that come as what are referred to as diatomic molecules. So for example, hydrogen, the way it naturally comes is actually a gas as two hydrogens together. Oxygen naturally comes as two oxygens together. Nitrogen naturally comes as two nitrogens together. Fluorine also, chlorine, bromine, and iodine. So the way these guys naturally come is basically two hydrogens together, a couple of oxygens that are bonded together. This is how we find these things when they're by themselves in their elemental form. They come as these guys. Since there's only two, these are also sometimes referred to as diatomic molecules. Di meaning two, atomic meaning atom. So it's a molecule made up of two atoms, basically. Now, what confuses people is each of those things that I just listed up there, they are elements and they are also molecules. So they are elements and they are also molecules. They are still elements because the only element present in H2 is hydrogen. So it's all the same element. So that's why they're still considered elements. And they're considered molecules because, frankly, they meet the basic definition of there's two or more atoms together. And that's basically what a molecule sort of is. Any questions on that there? So are these guys here a compound? Now, a compound, my hands work there. Try that again. Compound. There we go. A compound is a combination of two or more atoms from different elements. So a compound actually is a combination of two or more atoms of different elements. So by that definition, are these guys here compounds? They're not, and that is why they are not compounds, because they're all made up of the same element, and that's why they're elements and not compounds. So what is a compound? Well, something like, say, water, a little H2O action there. That's a hydrogen, a oxygen, and a hydrogen. That is definitely some atoms of some atoms of different elements together. So that would be a compound. That would also be, you know, something like CO2, which looks something like this, carbon dioxide. By the way, carbon dioxide, right, is dry ice, right? And that actually goes from solid directly to gas, skips the liquid part. Dry ice is not really water, it's actually carbon dioxide, and very, very cold and will burn you if you touch it, right? These both are compounds. Are both of these guys molecules? They are also both molecules because, again, they do meet the definition of there's at least two or more atoms together. In this case, the two or more atoms actually are different elements. It doesn't matter. They're still molecules. Is water and CO2 an element? Water and CO2 would not be an element, right? Because they actually contain two different elements in there, so they cannot be an element. So element is really the basic building blocks. It can only be one thing if it is an element, right? It's either like carbon, it's like oxygen, it's like nitrogen, and so forth. So a molecule is really, you can think of it as sort of a basic definition of you just minimally need two or more atoms together. They could be the same elements or different elements. A compound has to be two or more atoms of different elements that come together. And that, again, is the difference between those two. Any questions on that there? Okay. Outside of these, and you should know, by the way, these guys here that are diatomic molecules, and these are also elements. You should know that these elements here come as twos. By the way, all other elements on the periodic table are what are referred to as being monoatomic. They come as ones, basically, yeah. Uncombined, they come as ones. While we're talking a little bit about the elements there on the periodic table. If I take an element on the periodic table, and I'm sure you maybe know that some things do have charges, right? Do those guys have charges if we just take the element by itself? The answer is it does not. So if you have any type of element that's just by itself, it does not have a charge. As we'll talk about when we talk about sort of bonding and naming, things really only get charges when they kind of hook up together. And mainly what happens is when a metal and a non-metal element come together, that's when things get charges. But sometimes people, when they think about, you know, and we learn this when we talk about naming and stuff like that, like sodium, for example, always makes a +1 charge. They sometimes think if you have sodium by itself, it always should have a charge, and it doesn't. So if you have any element by itself, uncombined, they do not have charges. They're neutral. And again, things really only gain charges when they really start combining to form compounds and things of that nature, or molecules and stuff like that. Any questions on that? All right. Let's get that real quick here. Let's talk a little bit about the scientific method here. So the scientific method is really a method that's used in science like chemistry. And really, for the most part, the scientific method pretty much all starts with observations. And observations is usually the key to continuing on and doing some type of research, especially if you're a student in somebody's lab, you can tell your boss there, you observe something, they say, great, go do an experiment, right? And maybe you don't want to tell them that sometimes, but that is what happens. So when we do see an observation or make an observation, a lot of times what we want to do is maybe sort of figure out, you know, why is something happening? And that usually leads to a hypothesis. And a hypothesis is really, or a good hypothesis is really a testable sort of explanation for what you observed. The idea there is it's something that you could go do some type of test, like an experiment, to see if perhaps you could observe that again, or if that was the cause of whatever you were observing. So that often leads to, obviously, as I mentioned, experiments. And a couple of things occur. Usually, what occurs if you're doing some type of research is you go, I didn't maybe observe what I was hoping for, but I observed something else. Then you go tell your boss, and they go, "Cool, go do some more experiments and try it again." So it can be a sort of a vicious cycle sometimes of sort of observations, hypotheses, experiments, and stuff like that. Eventually, you hopefully will lead to some type of conclusion at it, as you can see here, where perhaps you could have a theory or a law. So hopefully you will end up with either maybe a theory or a law. And there really is sort of a difference between those two. And the difference between those two is pretty much this. A theory is sort of a explanation of what you observed, but it may not always be 100% correct in all aspects, under all situations. It is actually something that can be maybe revised as future experiments take place, and can be rethought of. So, for example, Dalton's law of atomic theory, there's two parts of it which perfectly apply still today. And there's two parts that were later shown, maybe not so much it's correct. Something like Bohr's theory of the hydrogen atom also worked wonderfully well for like hydrogen that has one electron, but kind of fell apart as you moved away from hydrogen and there was multiple electrons happening. So theories, can be very good. They can sort of explain what's going on, but they can be revised. There can be parts of it that is found, doesn't really occur, or maybe it's not so correct. And that's different than when something sort of gets locked into a law. A law is something that pretty much, no matter what the situation, always occurs exactly the same way. Like the law of conservation of mass. So if you do some type of chemical reaction, you don't lose anything along the way. Nothing gets lost. You should have the same amount of products in the reaction than the reactants that you started with. What that means is that really one of the reasons why when we get to, say, balancing equations, why we want to make sure if we started with like 6 carbons in the reaction, we should end up with 6 carbons in the reaction on the other side of the arrow. The only difference is those carbons may end up in some different compounds and molecules on the other side than where they started. But because we started, for example, with 6 carbons, it has a mass of 6 times 12, whatever that may be, 72-ish. We should end up with those same 6 carbons and different things on the other side, which also still has the 72 grams of mass. So that's the idea of something like conservation of mass. Also the idea of conservation law of energy. We don't create energy nor destroy energy. We think of energy almost like a perfect sort of transition, which means if something gives off a certain amount of energy, there must be something out there that will pick up that exact same amount of energy. So if you light a Bunsen burner, it's giving off a lot of energy right through the flame. All that heat and energy is now being absorbed by the surroundings, right? So all that energy is never being lost. It's just actually being moved to the surroundings. So there's sort of a perfect absorption and release of energy that occurs. Even the same example with our ice cube example, if you take an ice cube out, it's going to pick up all that heat and energy from the surroundings, and all that heat and energy will then end up in the ice cube. It's not lost anywhere. It's actually going into the ice cube, and it's used to do some type of work, right? The work it's doing, it's starting to melt the ice cube, right? And it starts to become liquid water. So these are laws, and it always occurs that way. So laws are more like pretty well defined. There's kind of like no exceptions. This is the way it happens. A theory is a pretty good explanation of what's going on, but definitely can be revised as time goes on. Any questions on any of that there? All right. All right. Some of this, and we're going to skip over a little quicker, is just sort of an introductory, the first chapter here. Some math skills, obviously, in chemistry is really important. For any number, we can identify sort of where everything is. So the 2 is the thousandth place, hundredth place, tens place, and ones place. We also have decimal places, right? The first one is the tenths, the hundredths would be here, and the thousandth place would be there as well. All right, so if we look at this one here, 15.24 grams. The 1 there's the 10th place. The 5 is the ones. The 2 is the tenths, and the 100th place there would be the 4. Positive and negative numbers. We do deal with positive and negative numbers sometimes in calculations, and it's important to remember that the sign is important, and it does mean a couple of different things, right? So obviously, if you have a positive number plus a, I'll go do this way, plus a negative number, we're really subtracting here, right? So we're going to basically be subtracting the two numbers. If you have two negatives, right? We will add them together, right, and end up with a negative number. If I have a negative plus, same thing, we'll try again. If I have a negative minus a positive, that negative, that minus in front of the positive turns it really into a negative number, right? And then you could add them together at that point. When we multiply negative numbers together, we end up with positive numbers, right? And if we multiply a negative number and a positive number, we end up with a negative number, right? All right, to make sure. Same thing on division, right? If we divide two positive numbers, we end up with a positive number. Divide two negative numbers, we will actually end up with a positive number. And if we divide a positive and negative number, we'll end up with a negative number, right? All right, so we got those guys, I think. More important, this is a calculator, and how to use it is really, really important. So let's talk about some important calculator type buttons, if you will. Let's talk about exponents and scientific notation and how to kind of put those into your calculator. First off, scientific notation is a process. Talk a little bit about here, since it's a calculator, it's a good picture we could use maybe. Scientific notation is a way of writing numbers when we have really, really large numbers and really, really small numbers. So if we have really large numbers and really small numbers, there's probably a good chance there's a lot of zeros in those numbers, perhaps. And if you try to keep the whole number the way it is and you got all those zeros, you probably will lose a zero along the way. So if we take n times 10 to the n is the general format of scientific notation. The big N here is a number between 1 and 10. And that's really important. So that first number in scientific notation should be a number between 1 and 10. It should not be 10, 20, 100. It should not be point something. It does need to be a number between 1 and 10. The small n here is a whole number that can be positive or negative. And it depends on really which way you sort of move the decimal point. So for example, if you got 1362 and we want to write that in scientific notation, we would assume the decimal points here. We would go one place gets us 136. So that is not a number between 1 and 10. We go here, that's 13.6, which is still not a number between 1 and 10. We do need to go one more place, and we would write something like 1.362 times 10 to the 3 here. I lost track there. 3. And that would be proper scientific notation. If we had a number like 0.0432.5, we would go 1 and 2 places to get us to a number between 1 and 10. And at this point, we would end up with 4.325 times 10 to the minus 2. Now, for the most part, if you move the decimal place to the left, it's going to be a positive exponent. If you move it to the right, it'll be a negative exponent. Or if you want to remember it this way, if it's a large number, it should have a positive exponent. If it's a small number, it should have a negative exponent. Obviously, you would do the opposite if you wanted to go back the other way. So it's really important to know how to write things in scientific notation, as we'll talk about when we officially talk about, I think, sig figs and all that good stuff. One of the only ways sometimes that you could actually get the answer to the correct number of significant figures, which is really what you should aim to do when you write things, is to actually write it in scientific notation. And that is because when we write a number in scientific notation in this sort of format here, all the numbers here that comes before the times 10 part, they are always significant. So if you see a number written in scientific notation, those numbers are important. They are basically significant figures, and we'll talk about what those are a little bit later. But they always are the significant figures. Now, more importantly, a calculator you should know how to use. And a lot of people screw up on calculations because, frankly, they do not know how to properly put the stuff into their calculator. So since we're looking at a calculator here, one thing that comes to mind that people do very commonly in this class that ends up with sort of a wrong answer is when they get to a situation, and by the way, you can look through these if you like, how to properly punch things in. I'm just gonna look for somewhere to scribble. They come across a situation where maybe they got a bunch of numbers like 123, 4.25, 6.5. Then they're going to divide those numbers by, say 32.5, 624, 132.5, and so forth. And what happens a lot of times is everybody wants to punch them all into their calculator all at once. So they'll punch everything on the top, they'll hit the divide button, they'll put in all the numbers on the bottom. And then they're very much surprised, like, hey, I just got the wrong answer. I don't understand it. And depending on what calculator you're using, if you do not put parentheses where they should go to tell the calculator how to properly do the calculation, we sometimes think calculators are smart. They're only as smart as how they are programmed, by the way. So you have to be smarter and tell the calculator, this is how I would like my calculation to be done. And if you don't put parentheses in there, you will get the wrong answer. And I see it happen a lot. People just want to put that entire thing all at once into their calculator. If you want to take some advice from me, that I've done this once or twice, I would do it this way if I was to go and actually punch that into a calculator. Up on top, what we're basically doing is multiplying, right? And you can take as many numbers as you like up on top. If all you're doing is multiplying, you can punch all those numbers into your calculator all at once. What you should do when you get to the very end of the top is actually hit your equals button. Yeah, so you should actually hit your equals button at that point. Then what we really want to do is go back and divide by each of those numbers that are there. The beauty of math is they are technically all being multiplied together, which means they're all being divided by the top number, which means you could actually divide everybody individually by the bottom number. I would hit equals, then I would divide it by 32.5, and then I would hit equals. I would divide it by 624 and then hit equals. I would divide it by 132.5 on the bottom and then hit equals. I guarantee if you do it that way, you will never get the wrong answer. Well, provided you punch everything in correctly, but you'll never get the wrong answer if you do it that way. I can't tell you how many times I've seen people try to do that bottom thing all in one calculation, and they always end up with the wrong number. And you could do it all at once if you know how to properly put parentheses, which means you really kind of parentheses up everything on the bottom there in one sort of calculation, so the calculator knows, oh, all those numbers come together and they all should be multiplied. So if you want to do it safe, I would definitely kind of take that approach. And we come across this a lot, especially when we're doing dimensional analysis and we set up these problems to show the units canceling. We end up getting a lot of numbers like on top that we need to multiply, then we got to come back and kind of divide by a bunch of numbers on the bottom. So it's really important to make sure that you actually know how to properly put it into the calculator, right? Especially if you know how to do the problem, you don't want to miss it because you just don't really know how to punch it in correctly. So I'm a big fan of using the equal sign and doing a little bit in parts, and you should always get the right answer. Like I said, if you got a million numbers on top, you can sit there all day and put as many as you like, as long as you hit that equals at the end, and then individually go back through and divide by all the bottom numbers. Any questions on that there? By the way, there's some important buttons on your calculator. Since we're kind of speaking of calculators, we talked a little bit about scientific notation. This button here is also a really important one. On most calculators, you have a button like that, or you got a button like that. And those are what I call like your negative button. Some people is like the change of sign button, whatever it may be. But it's what you want to use if you have a negative number. You don't want to use the subtract button or anything like that. That is the dedicated button to put like a negative value into your calculator. The other really thing that people struggle a lot with is actually the scientific notation. So say we had a number like 6.25 times 10 to the minus 4, and we wanted to actually put that into our calculator correctly. There is actually an exponent button on most everybody's calculator if it is a scientific calculator. And your variety of exponent buttons, to my knowledge, is there is an EE button. There is a EXP button, maybe. Or if you have some of the fancy newish calculators, I like to call them like the two-tone calculators. They usually have like one color and like a different color on the edges. They also actually will have a button that's like a times 10 to the n button. If you're not sure what type of calculator I'm talking about, it usually will also have a little wheel on it that kind of looks like this. Yeah. So if you got one of those calculators, we'll talk about you in just a second, what you need to do. These are very common ones for exponents as well. So what people do when they try to put a number in scientific notation into their calculator is, frankly, they do all kinds of weird things. They try to use like the second log button. They use a little caret action. They use some multiplication buttons. And frankly, you shouldn't use any of those buttons because that's not really what they're for. So anything in scientific notation should actually go into here. If you were to properly punch this into your calculator in scientific notation, you would go 6.25, and then you would actually hit the exponent button, whichever exponent button you got going on. If you do that on most people's calculators, it will show 6.25 and maybe pop an E next to it. It may show 6.25 and pop a couple of zeros up on top. Maybe it says times 10 to something underneath it. And those usually what you get when you hit one of these two buttons. Again, I'll talk about this button in just a second and what you will see. At that point, when you hit that exponent button, it actually represents this part of the number, the times 10 part of the original number. And that is why you do not need to hit the multiplication button. You do not need to hit anything else, the caret button, the inverse log button. You don't need to do any of that unless you would like to get the wrong answer. So don't do any of those things. So when you hit that, that represents the times 10 part. What's left is really the minus 4. So again, this is the part where we want to make sure that we use our negative button, not the subtract button. So you would hit the negative button, whichever negative button you got going on there, and then you hit 4. This then will turn this into negative 4. This will turn this into negative 4 as well. And that is the proper way to enter into your calculator 6.25 times 10 to the negative 4. First off, any questions on that there? I know you're asking what happens if I have the other calculator. You should throw it. No, I'm just kidding. Don't throw it away. So what happens if you have the other type of calculator? The only difference is you actually do, speaking of parentheses, because of the way those calculators are typically programmed, you do need to put parentheses around every number that you have to put in scientific notation. So if you have a calculator that has these buttons here, what you would actually do is you would hit the parentheses to open a parenthesis. And then you would do very much similar to what we did on the other type of calculator. You would type 6.25. You then would hit your exponent button. At that point, when you do that on your calculator, it will look something like this, 6.25. It will do the times 10. And then you'll have like the blinking cursor button up there up on top. At that point, you can then hit the negative button and 4. And what it will then make your calculator look like is 6.25 times 10 to the negative 4. And you will still have your cursor up on top blinking at you. Now, you will be tempted to close your parentheses. And if you close your parentheses with your cursor still up on top, it's going to look funny and it may not work because you'll get like a really small parentheses up there on top. And then your calculator will have no idea what it's supposed to do at that point. So that is where the little wheel comes into play. With your cursor up on top, you need to hit the right button there. And what that will do is bring your cursor back down to regular size. And now you can finally close the parentheses. And you have your number in scientific notation. So if you have that calculator, you really want to make sure that you put parentheses around all the numbers. It works perfectly fine. There's nothing wrong with those type of calculators. You just got to make sure you parentheses up every number that's in scientific notation. Otherwise, the way those calculators are programmed, they'll take your scientific notation number, and if you don't put the parentheses and you have that calculator, it'll break it apart into 2 separate numbers and it'll do the math wrong and you'll end up with the wrong number. So very commonly when you are doing some type of problem that involves scientific notation and you're not sure why it's wrong or you're not sure if you got the wrong number, the way you can figure it out is this. When you get your final answer, let's just say that this was not the number we put in, but let's just say that this was our final answer. What you typically see if you're kind of putting it in wrong is this number part right here will be all good, but you'll notice this number right here is just a little bit off, maybe by 1, maybe by 2, very, very close, but a little bit off. And that's usually a very good indication that you are not punching it in correctly. It is really important to be able to do that in this class. There's a lot of numbers that are in scientific notation that you need to be able to punch in there. When we get to a later chapter, when we talk about sort of acids and bases, there's a lot of numbers that are nothing but scientific notation, and it also involves the log button. So you got to be able to kind of punch those guys in correctly. Any questions on that? By the way, if you're not sure still where your exponent button is, just at some point come down and see me. I'll show it to you and how to use it on your particular calculator. All right, so why don't we try one since we talked it up, all that good stuff. We'll just skip the percentage luck over here. But let's say we had 4.25 times 10 to the minus 8. And let's divide it by 1.2 times 10 to, how about 16? All right, see what you get. I'll do it as well since I just made it up. So try to use, again, the exponent button. Don't use anything else there. It's incorrectly, you should put into your calculator 4.25. Obviously, if you have the other calculator we talked about, then you should start with the parentheses. You then should hit your exponent button. And this is -8, so we will hit our negative button. We will hit 8, and that is the proper way, again, to punch it in. And if you have that other calculator at the end, you should parenthesis 4.25 exponent -8, hit the little circle on the right, close your parentheses. Yes. We then would hit our divide button. We would go 1.2 one more time with the exponent button. In this case, our exponent's actually positive, so we don't obviously need the negative. So all we have to do is hit 16 and our equals button. There we go. And if you do all that good stuff, you go 4.25 exponent button, negative button 8, divided by 1.2 exponent button 16 equals something. Getting old, but I think it's 3.5. I'll just write all the numbers, not the right way to give the answer, by the way. Times 10 to the minus 24. I think that's what it says. There we go. We clearly would round this down a little bit, but I just want to make sure you kind of saw the numbers there. Probably something like 3.5 times 10 to the minus 24. And we'll talk about how you do that and why you do that a little bit later on. But that's what you should get. A couple of things that is very common as well that people do in this class and all kinds of classes is a lot of times on most people's calculators, you know, sometimes like mine here, they threw a bunch of numbers in there, right? And like the exponent part's like squished over here on the end. And it's very common people will write just the front number and forget to actually put the like times 10 to the minus 24 part. So you want to make sure that you don't forget that part of your answer. By the way, this is the proper way to write a number in scientific notation. This way is not proper. Don't use the E, even though the E does represent it, but you should write it as times 10 to the minus 24. Once again, if you find yourself with like the 3.5 part good, but the minus 24 part not so good, is probably the way you put it in. Yeah, that is probably the answer there. Any questions on that? Again, once again, if you need help with that, just come on down at some point, discussion, whatever, and I'll be more than happy after lecture, whatever you like to do. I'll be happy to show you where your button is on your calculator. Any questions on that? That I think is a very, very challenging thing for a lot of people. Also, a couple of things about scientific notation and significant figures as well. You should always try to give the answers to right numbers, significant figures, which we'll officially talk about in chapter 2. But your calculator obviously doesn't always give it to you in the right number of digits. It also may not give you your answer in scientific notation, right? It may just give it to you in decimal form, unless you have your calculator programmed to give you everything in scientific notation. So, you know, your calculator doesn't necessarily always give you the answer maybe the way you want it or round it to the proper digit. I could probably guess and tell you that if you're laying up an answer like this with 40 million numbers, you should probably find some rounding soon, yes, and not give me that many numbers, yes, where it starts on the front of the page and wraps around the back of the page, all the numbers. So don't do that. I've had that once. Like somebody wrote numbers and it kept going, it kept going. I'm like, wow, this is the longest amount of numbers I've ever seen. And then I think he realized like, uh-oh, I'm running out of room. So it got really like squished in there at the end. I'm like, you know, edit yourself somewhere. Yes. Take out some of those numbers. All right. Any questions on calculators there? That's kind of important. Obviously percentages here that I scribbled all over is important as well. A lot of times we do get numbers that are percentages, you know. For example, if we had, like it said, maybe our 4.5% by mass, say sodium chloride, for example. A lot of times if we have a percentage, we could kind of really turn it into a usable sort of number by assuming that we have how much of something. The easiest way to convert a percentage into like a usable number is to assume you have 100 of it, right? That means the number stays the same, right? If you got 80% on your exam, you probably got 80 points out of 100, right? If you got 90%, you got 90 out of 100. So a lot of times when we want to kind of convert a percentage into sort of a usable number, we assume 100. You can really assume as much as you want, but the numbers change. So we want to kind of keep the numbers the same. So if we had something like this, we could say that we would have something like 4.5 grams of sodium chloride and like 100 grams of solution, for example. Or this is really a conversion factor, which is really a fraction, right? A numerator and denominator. And we could also use it as like a conversion factor by just simply flipping it around. 100 grams of solution would have 4.5 grams of sodium chloride. I think the example on the previous page was tennis balls, I think, right? So if we had 5% red tennis balls, that means every 5 balls out of 100 would be red, right? And that's why it's 5 red balls out of 100. And we could use it as a conversion factor. If it was 50% green tennis balls, for example, every 50 balls out of 100 would be green in that particular case. So that is something that's very useful, and we do see it, especially when we get into sort of solutions and stuff like that. Sometimes you're given things in percentages, and you want to kind of turn them into conversion factors that you could use to help you solve things. In general, rearranging equations and formulas is something that we do in here as well. So really, when we have something that is like an equal sign, and we have things on opposite sides of the equal sign, basically what happens is if you move something across the equal sign, it ends up in the opposite location, basically, right? So when we get to, say, gas laws, for example, if you have, like, say, V1 over T1 is equal to V2 over T2, and maybe you are looking to solve for just V2 by itself. In this case, what you technically would do, mathematically speaking, is you would multiply both sides by T2. Those guys would cancel, and you would end up with V2 is equal to T2 V1 over T1. The quick way is basically just move things to the opposite location. So I want to solve for this guy, which means this guy needs to move. He just moves across location. He's on the bottom on the right. He ends up on top on the left. If I wanted to solve for V1, if I want to solve for V1 in this case, we would take T1 and just move it to the opposite location up on top. And V1 would equal V2 T1 divided by T2. So being able to properly rearrange equations and formulas is really important for success. Basically, whatever you move basically across the equal sign, you're really doing the opposite function, if you will. And that's really what we're doing here. When we have V2 divided by T2 over here, we're dividing, right? So to get rid of the guy on the bottom, which is being divided, you need to multiply. The opposite function basically brings it to the other side. If you have something like what we got there, 2x plus 8, yes, it says plus 8 is equal to 14. Basically, here we are adding, which means to get that to the other side, we need to subtract. So we would do the opposite. We would subtract this to both sides. Those guys would go away. That would give us 2x is equal to 6. I'm trying it without the calculator there. That gives us 2x is equal to 6, basically 2 times x, right? And we want x by itself. So the opposite function would be to divide, right? So we would divide both sides by 2. Gets rid of the 2. X will now equal 3 in this case. So pretty much you could think of the equal sign as basically whatever you move to the other side, you do the opposite function is how you get yourself to the other side. If it's more just fractions, you can move things to the other side and they end up in the opposite location. Any questions on that? Now, when we look at this and we want to solve for P1 in this case, so we have P1 V1 is equal to P2 V2. Now, if you want to do just a quick move it to the opposite location, even though these guys are not really written as a fraction, they basically are over 1, which means that V1 needs to go to the other side on the bottom, and you will end up with P1 is equal to P2 V2 V1. That's basically dividing both sides by V1. Once again, the real math of it is we're multiplying here. So to get it to the other side, we need to do the opposite, which is divide it to the other side is basically what we're doing. Any questions on that there? So that is also something that's sort of a sticking point for a lot of people is just the rearranging of the equations. So if that's an issue, you know, a lot of that does come in the gas sort of law chapter. There's a lot of sort of formulas that need to be rearranged. There's some formulas along the way as well that you sometimes need to solve for different things. But the one thing you just think about is basically opposites. So opposite locations, opposite functions, gets things to the other side of the equal sign. Any questions on that there? Graphs, we're not going to pretty much interpret graphs too much here. I guess our official scientific notation we talked about. All right. So again, in the notes, sort of what we talked about, I guess I was a little ahead of the slides there. Our scientific notation, again, there's your common exponent buttons as we were talking about. All right, so why don't you try these here, write each of these in correct scientific notation. Okay, let's take a look at the first one. So although it's not written, we would assume that the decimal point would be there. So we would go 1, 2, 3, and 4 places to the left. That would give us 6.4 times 10 to the 4th. There is a reason why we left off the zeros, and it's because they are actually not significant in this case. As we talked about before, significant figures are any of those numbers before the times 10 part. So this number, and we'll talk about it in chapter 2 there, has actually 2 significant figures, and that would maintain the same 2 significant figures. So it's really important if you are sort of moving a number from scientific notation to decimal or back, that you really don't lose any significant figures along the way. You're just sort of transforming it into another way of displaying the number. Looking down here, we would want to go 1 place and 2 places there. That gets us to 2.1 times 10 to the minus 2. Again, you can see the top number there was a larger number, so we have a positive exponent and a negative number for our smaller number. Any questions on either of those two? Now, if we did have a number in scientific notation, say like 4.52 times 10 to the minus 3, and we actually wanted to go to decimal place, a couple of things could help us decide what to do. First off, the number tells us really how many places we need to move the decimal place. The negative also tells us that when we're all said and done, we should end up with a small number. So that could help you decide which way you should go. We would actually need to go to the left here 3 places. So 1, 2, and 3 places, because then we would put zeros in front of that and make it a small number. If we went the opposite way, we would put zeros at the end, which would make it a larger number, which is what it should not be. So in this case, we will end up with 0.00452. This is also very proper and a really good idea to do, which is to put the 0 in front of the decimal place. That allows not all your numbers just to run together. Yeah, so you clearly see that's a separate number than the number before it. So is it technically wrong if you do it this way? Technically, no, but you might run into some trouble there. So I would not leave that without the 0, and make sure that you put it there so you don't mess it up. And then obviously if we had something like 3.2 times 10 to the 2, in this case, the 2 is 2 places. It's a positive exponent. So we want to make this a bigger number. So to make the 3.2 larger, we actually would go to the right in this case, right? And we go a couple of places. There we go. And we'll end up with 320. Any questions on how to go back and forth between scientific notation and decimal place there? Looks good. I like it. All right, that is chapter 1. We'll wrap it up there for today.